Hello viewers and welcome to another episode of Space Science with Python. Now, with today's session we are starting a new small project on near-Earth objects, or short called NEOs or NEOs. And we are not doing any coding today, but I would like to give you a small introduction into this topic of near-Earth objects. Of course, it's a very huge, vast topic, but I would like to give you the quintessence of the NEOs, and also a little bit what we are going to do in the next couple of weeks. Now, you may remember the 15th February of 2013, this picture here, a meteor from the, or a picture of the meteor from Chelyabinsk in Russia. And it was, I think, around 17-meter diameter asteroid or near-Earth object that hit the Earth. And yeah, it exploded in the atmosphere, caused a shock wave, and windows were shattered and so on. Fortunately, no person died at this day. I think a few were injured by the shattered glass and so on. But this was one of the most recent asteroid impacts on our home planet since the Tunguska event in the beginning of the 20th century, which was over 100 years ago. And the point is of this object, we didn't see it coming actually. Although we know over thousands of NEOs out there, we were not able to determine or to discover it before. And you may also ask, well, why didn't we see it in the evening before with a telescope? Wasn't it a bright dot or something? Well, in this case, the reconstruction of the orbit showed the following. So we have here the Sun in the center. We have here Venus orbit, so Mercury is missing. And here's the Earth orbit, and this was the orbit of this near-Earth object. And it came here from the inner part, so it was within 1 AU, and so to speak, it came, or it flew to the Earth from the sun direction. So yeah, telescope weren't even able to detect it. Of course, if it would come from the other side, maybe the day before or a few weeks before, you would have seen a small speck, light speck in the night sky and determine a trajectory and so on, because this has already been done with smaller NEOs that hit our planet. I think 2 or 3 NEOs with a size of around 1 meter were discovered a few hours before impact. So this is theoretically possible, but in this case it just came from the sun direction. And of course, it's only, not only, but it's one object of many objects that are revolving around the sun and that come close to our home planet. So here's a small list of current close flybys of NEOs or astro objects that are approaching our home planet quite closely. And you may ask, well, here is written asteroid, is it now a near-Earth object, or what's the definition? Well, the near-Earth object can be anything that is, that approaches the sun within 1.3 AU. So it's not really a definition based on some, I don't know, it's not like distinguishable between a sun and a planet, for example, in this classification schema. It's more like an artificial boundary or artificial limit that says, okay, every object that that approaches the sun within 1.3 AU is a so-called near-Earth object. And in this category, you have, of course, asteroids, you have, of course, comets, but you have also artificial objects. So, for example, some old rocket stages from the Apollo mission are also classified as an NEO, actually. So this is quite interesting. And here you see some asteroids with a missed distance in this month, and also to June to July, known objects. So here's the designation number, and you see here the date of the closest approach and the missing distance. So 1 LD is the lunar distance, so the average distance between Earth and the moon. And you see here, for example, I don't know, what's today's date? 22nd of May. So yeah, in 2 days we have an object with a size of around 16 meters. So this is like the the Chelyabinsk meteor size that is having a close flyby at 2.6 LD, which is like around, I would say, 1 million kilometers. So yeah, it's not really critical, but yeah, on astronomical scales, it's quite close. And yeah, and the question is, of course, okay, how many NEOs are there and how many are still undiscovered? And this is something I would like to talk with you in this very short introduction on NEOs today. So let's go to the next slide. And what we see here is, again, the sun. We see here Mercury. We see here Venus, the Earth in blue, and Mars. And each dot here is a known object. Yeah, an asteroid, NEO, whatsoever. If we play it, you see there is a lot of movement going on. But yeah, you shouldn't be concerned or something, because of course the space is huge, right? I mean, here between the sun and Earth we have 1 AU, 150 million kilometers. Here we have also, we are projecting in 2D, so on the ecliptic plane, so all the movement in 3D is gone. And of course each dot is not like a kilometer size object, it's also like maybe 10 meters or 5 meters, so also various sizes. And of course you see that some of these objects, they are behaving quite good. Yeah, they're not really coming into the inner part of the solar system. They are part of the main asteroid belt. And this kind of images are always this kind of confusing images that you see also in the sci-fi movies when people fly through an asteroid field. It's extremely dense and so on, but you have to avoid a collision. But in fact, the main asteroid belt, you could fly through it and you wouldn't hit anything. So it's really not a dense region. What you may see here, though, is these small red dots here, yeah, in this animation. I think this is from the Minor Planet Center. Just the bar here is hiding the credits, and you see that there's certain density. There's a certain density around the Earth. You see here more dots around Earth, and you may ask, okay, is this some kind of I don't know, is this a natural behavior or so, that we have a lot of objects approaching us and revolving around us or having close encounter? Well, this is of course an observational bias. I mean, we live on the home planet Earth, and we observe everything from Earth, and if there are close flybys with our home planet, we of course register it. If there is a close flyby with Venus or Mercury, we are not able to see it because, well, it's closer to the sun, smaller objects are fainter, and the same thing applies also for Mars. So of course we have here a certain observational bias. Now let's zoom out a little bit, and we see here now the asteroid belt now, in its vastness, so to speak. We have here also Jupiter and some populations called the Trojans and the Hildas. Oops, I should go back. And we see here, of course, here again the small, denser cloud of objects revolving around, or not revolving around, but approaching the Earth. And of course, this is now the question. So how many objects are there? How many objects are out there, especially at the NEOs? So NEOs, these are not NEOs, also here not, because they are not coming as close as 1.3 AU to the sun. So these are like the main belt asteroids, and these are like the Trojans and so on. So let's move to the distribution of NEOs. And what we see here is the cumulative number of discovered NEOs versus the discovery date. So in the beginning, in the 80s, 90s, we didn't see a lot of these objects. We didn't know them. And starting in 2000, with more and more surveys, we observed more and more objects. So you see here, it's like we have 3 bars. One is for objects larger than 1 kilometer, one larger than 140 meters, and then all objects. And what you see is that especially the larger objects, it appears to be saturated. So maybe we discovered already all 1 kilometer size objects, so all planet killers, so to speak. The larger ones, also with 100 meter, they can have a devastating impact on our home planet, so either causing a tsunami or destroying cities and so on. So you see still see some kind of linear increase of discoveries. So we are probably not at the end. And for all objects, so also 5 meters and so on, you see with all the surveys and improving telescopes, the discovery rate is almost exponentially growing. And I, for myself, I also worked on NEOs for my bachelor thesis. Bachelor thesis was back in 2012, so somewhere here. And I remember it was almost 10,000. So I think like something like 9,000 or something like that. So until up to now, in the last 10 years, this number increased by a factor of 3. And we are still discovering more and more objects every day. So pretty impressive about this distribution. But the best question is, of course, what kind of scientific project can we now do with Python, right? I mean, there are a lot of surveys, so is there actually any tasks? Should we build up our own telescope and observe NEOs? Well, first of all, in the next couple of weeks, I would like to make a small NEO deep dive with you. So we will download the current NEO data. We will check also the subcategories. Yeah, there are certain names for NEOs like Amor, Apollo, Aten, and so on. And we will just take a look what are these different definitions. Take a look at the statistics and also create our own plotting or animations, as you saw just before from the Minor Planet Center. We will do it by our own with matplotlib, but we will also use Plotly, for example, or Dash to really also create interactive also animations and so on. So yeah, it's a little bit more about data visualization, of course. And we will also talk later about simulated data. So yeah, artificially created NEO populations. And why is this important? Well, at the end of the day, I do not want to just do some plotting around. It's really interesting or important to have a certain scientific objective or task. And my question is, okay, is there a way to optimize our or a NEO observation strategy? So can we improve or increase the output of discoveries? This sounds maybe a little bit strange, but let's think about the following. We have NEOs have a certain brightness, we have a certain telescopes with certain sizes and exposure time and cameras and so on. And we can vary all these parameters and also where we look and so on for how many seconds or minutes. And this will reveal a different picture or a different, different sensitivity to NEOs depending on their size, their brightness, and so on. And this is something I would like to optimize with you. Of course, this is like a small science project, so you have to be aware of one important thing. We are not creating a paper, and we are not submitting it to any peer-reviewed journal. So, yeah, always, if you find an issue or bug, always write in the comments, because this is what science is all about discussing these things and also making a review of solutions, of computations, calculations, and so on, of theories. Yeah, because we are not creating a paper and not letting it being reviewed by another scientist. It can also be that what we do at the end of the day is also a little bit, slightly wrong or not 100% realistic, but we will try to give our best. And how are we going to do this? Well, first of all, as I said in the beginning, we will try to understand the current NEO population. We will also obtain simulated NEO populations because we need a population that is unbiased based on some kind of theory, some kind of numerical simulations. Otherwise, we have this biased NEO population, and then we try to optimize observation strategies for a NEO population that we already know. So we need a simulated population. We will visualize the NEO distribution as seen from the Earth, considering the brightness of an NEO. So the brightness corresponds to the size, to the surface reflectance, the distance, and also the angle between Sun and Earth. And also considering telescope and camera settings, the properties of the camera, exposure time, and so on. We will also consider the geolocation. So you have a horizon, so you cannot see the entire sky all the night. And also considering the known distribution. So if we have the detection distribution of our artificial NEOs, we have to, of course, consider the known NEO distribution. So, for example, as I had said, it's very likely that we found all 1 kilometer sized NEOs, so we have to subtract them, and so on and so on. So you see, we can theoretically create a very huge and vast project on these near-Earth objects. And it's a little bit more of a simulation or numerical task, so there is no machine learning going on this time. I'm currently also preparing some machine learning tutorials for the project afterwards, but this time I would like to talk more about NEOs, and so that some of you who are not maybe familiar with machine learning or don't want to work with machine learning because they are more focused or interested into space science, they will find a very nice project here in the next couple of weeks. So yeah, follow me with this journey of determining the perfect or the most optimized NEO observation strategy. So we can then, hopefully create some kind of results that will help us to find as many, near-Earth objects as possible. Okay, so next time we will start with the download of the data and doing some first statistics. So I hope you're eager to dive into this topic. It's really interesting, I can tell you. It's people always say, smaller objects in a smaller system, is it really interesting? Well, talking about NEOs and these objects that approach our home planet quite closely is quite interesting, I have to say. So I hope you're looking forward to it. And until then, I wish you a very nice week. If you still need some time for the other code parts, now you have the week to do it because there's no coding session today. And I wish you a very nice week and talk to you next week.